Hello everyone, welcome to part 3 in our series on the derivative. Today we're going to be talking about the power rule. Okay, in a previous video we looked at the derivatives of these functions. Here was the function, here were the derivatives that we determined using the limit definition of the derivative. Okay, do we see any pattern here? One thing you might notice right away is that the power of x seems to appear in the derivative. Next, you might notice that the power of x over here in the derivative is 1 less than the power of x in the original function. So here we had a 2. That 2 showed up in the front, and the power of x in the derivative got reduced by 1 because this is x to the 1. X cubed, the 3 came down in front, and we got x squared. That even seems to work here. The 1/2 came down in front, and 1/2 minus 1 is x to the minus 1/2. That even works up here. If I reduce the power of 1, I get x to the 0. Well, that's 1. 1 times x to the 0 is 1. Finally, I get 0. Let's see if I use that same kind of pattern. 0 times x to the 0 minus 1. Well, that's 0. So if we were to guess at this point, we might say that if f of x equals x to the n, we think that the derivative of f is nx to the n minus 1. Well, in math, we can't just use a few examples and decide that, okay, this must be the right answer, because who knows, maybe another example comes along and this doesn't work. So we actually have to show that this is true. And that's what this video is all about. Okay, let's do it. Remember how we calculate the derivative. F of x is x to the n. F prime of x is the limit as h goes to 0 of f of x plus h minus f of x, and that is all over h. Okay. Well, let's use our function. Remember, this means substitute x plus h wherever I see an x. So I get limit h goes to 0, x plus h to the n minus x to the n. That's all over h. Okay, the tricky part with this calculation is this right here. What is that? X plus h to the n. N is basically any integer. It could be 3, could be 5, could be 12,000, who knows? Well, there's a very special theorem called the Binomial Theorem, and it tells us how to expand this quantity. It's exactly what it tells us. And it says, first, write x to the n. Next, reduce the power of x by 1 and multiply by h to the 1. And then the binomial theorem also tells us that we get a number in front, n. The next term looks like this, 1/2 n minus 1. We reduce the power of x again, and we increase the power of h again. Notice how these powers always add up to n. n minus 2 plus 2 is n. n minus 1 plus 1 is n. n, think of this as h to the 0. n plus 0 equals n. So that's kind of the pattern. It's probably, if you haven't seen the binomial theorem before, this is probably a complete mystery. Let's not worry too much about that right now. It's going to turn out not to matter as far as the derivative is concerned. Let's keep going. If I keep going here, I'm continuing to raise powers of h by 1 and reduce powers of x by 1 So eventually I'm going to end up with n x to the 1, h to the n minus 1, and our final term, h to the n. This whole thing comes from what we call the binomial theorem. And we're going to need it because we need to substitute x plus h to the n in our definition of the derivative. Okay, well this looks a little messy. It is, but bear with me, it's going to work out. Okay, so I've gone ahead. Here's our definition of our derivative. I've gone ahead and substituted what we just wrote down right here. That's that whole messy thing we just came up with. And I've also included minus x to the n on top of the function, top of this fraction, sorry. Giant bar there and an h on the bottom. Okay, this looks terrible, but it's actually not. The first thing we notice is that this x to the n, subtract this x to the n, those cancel. And now a crucial thing to notice, every one of these terms has a power of h. So I can divide every one of these terms by the h in the denominator, which as always with derivatives, when you're calculating using the definition, that's always the problem. That's why you can't plug in h equals 0 into this expression. You get 0 over 0. But now that I've simplified, h down here is going to cancel this h. It's going to cancel one of these h's. It's going to cancel almost all. It's going to cancel one of these h's. This is going to become h to the n minus 1. Let's see what we get. Limit h goes to 0 of, well, n x n minus 1. That doesn't have an h in it anymore. We still have 1/2 n minus 1 x n minus 2 times h plus plus h n minus 1. That's it. Look at what happens. Every term starting with this term and going on has an h in it. When I plug in 0 for h, they all disappear. What do I get? I get n to the x n minus 1. I'll write that result in red so that we know what we just got. If f of x is x to the n, then f prime of x is n to the n times x to the n minus 1 power. That's the result. Now, we prove this only for positive integer powers of n because we use the binomial theorem to expand this. The binomial theorem doesn't work like this if n is, let's say, negative or if n is a fraction. So right now, this is called the power rule. We're going to see later this power rule works even if n is negative and even if n is a fraction. But for right now, this is what we've got for integer n. That's it for this video. I hope you enjoyed it, and I'll see you next time.